All right, so here we're going over problem 2B.1 and Transport Phenomena second edition. Um, so yeah, here's the problem. Different choices of coordinates for following family problem. Just redefine the velocity or derive the velocity profile like you do in 2.2, but you replace the x with x bar, and it's basically you just move the x coordinate. Going to 2.2, where is it? So in this problem, the x starts here, but in our problem, it starts here um, at the bottom of the liquid and it goes up. So that's the only difference. And just show you what they got. That's what they got with X on the top. And for us, our target is this formula. And you'll see a mistake that I made. Um, I defined a momentum z flux, and that would give you a differential pressure. Obviously, there's no pressure in the expression, so that was wrong, and that's because the top of the liquid is exposed to air, so there's no differential pressure like from the bottom to the top. There's no differential pressure as a result because it's exposed to air. Like if this was a pipe and there was walls surrounding the liquid, there would be a differential pressure, but since there's not, it's not a pipe. There's not. That doesn't exist. So yeah, so we need a momentum flux and the theta or the whatever that symbol is, ZR direction, but in this I'm doing it in ZR and ZZ. So yeah, here's just some text. You can pause and look at that if you want. So basically, every momentum flux has to be applied on a face. So the momentum flux is changing in this Z direction due to Z and changing in the X direction. Or wait, no, that's changing in the Z direction due to X, but that's wrong. Z should be first. But it doesn't really matter because they're the same either way. But so they're facing, they're changing in a direction and they're changing due to another direction. And that the direction that is changing, so the X direction in this, which it's the wrong order, should be ZX. So this face, this WL face, is the face that's perpendicular to the X direction. So we go up to the drawing here. The X direction is going straight out, and so the face of the momentum is this face, which, if we go back to the drawing, that face is, where is it? Where is it? Let's go to the 3D drawing. And obviously the coordinates are different, but it doesn't really matter for this. So the face, it's looking up, and the face perpendicular to the x direction is this face, which is W times L. So this z equals L is equals 0, and then the y equals 0, y equals L. So that's WL. And then for this other face, it's not really prevalent to this problem, but it's interesting to know. Is there even audio on this? I think there is. Yeah, there's audio. Okay, so the other face, which is in the z direction, would be like this face here. So going back to that drawing again, that face would be this face here. So that's W times the delta x, because this plate thickness is delta x. So you would integrate over this face. You kind of just have to make the a differential area, and that's usually going to be like x or r if you're in cylindrical coordinately. Um, at least for these B level problems, there's all throughout this chapter. So yeah, going through that. So that's the WL, and then that's the W delta X, and then the rho G. So that's like the gravitational force that is multiplied by the volume. So the gravitational force is applied over like the whole object. So that's why it's WL delta x, because that's the volume of the whole object. And then this cosine B is because the thing is tilted. So obviously cosine would be the same B. Let's say cosine. Same side over. So it would be this. It'd be cosine. Yeah, so that makes sense. Cosine is, where is it? Where is it? Let's go to the 3D drawing. And obviously the coordinates are different, but it doesn't really matter for this. So the face, it's looking up, and the face perpendicular to the x direction is this face, which is W times L. So this z equals L is equals 0, and then the y equals 0, y equals L. So that's WL. And then for this other face, it's not really prevalent to this problem, but it's interesting to know. Um, is there even audio on this? I think there is. Yeah, there's audio. Okay, so the other face, which is in the z direction, would be like this face here. So going back to that drawing again, that face would be this face here. So that's W times the delta x, because this plate thickness is delta x. So you would integrate over this face. And you kind of just have to make the a differential area, and that's usually going to be like x or r if you're in cylindrical coordinates, but in this case it's adjacent over hypotenuse. Yeah, that makes sense. So that's just the momentum flux. So all the momentum fluxes, and then you add the gravity flux, and then you that equals 0, which I didn't put there because I'm an idiot. So next we just divide by volume so we can get a differential. So we divide by the volume, and which is again that WL delta x, and we just find that from back to the drawing. W, L, and then delta x, so that's the volume. So yeah, you divide by that. So now we got to define the momentum fluxes, and that's in 1.7-3A and B. So yeah, I guess I might as well just show you guys that. So it gives you these two formulas, and you could just insert any of the letters. So you could say XR as long as there's two different letters, or you could say Z, Y, X, Y, whatever for these, or Z, Z, Y, Y. Just it has to match. So use this second definition, because this tau is just um, it's just this definition here, which is the pressure times sigma times this, and that sigma is basically if they're the same, it's a pressure. If the x and x are the same, it's a pressure, and if they're not the same, there's no pressure. So this is where the definitions come from. So yeah, back to yeah. So momentum flux and the ZZ momentum, all these terms are going to be 0, because I just I just originally thought that there was going to be a differential pressure, but there wasn't. The this shear stress, those are defined in table B1. Okay, B1. So tau ZZ, so it's just this expression, but then this expression goes to 0 because um, we're assuming the fluid has a constant density. We're assuming it's Newtonian, so it's incompressible. So this whole term goes to 0, and it's just saying, yeah, the fluid. We're assuming the fluid has a constant density, so this term can be omitted. So yeah, so we're just doing this term out front, and if we go back, we say that that term goes to 0 because the z velocity is not dependent on the z direction, and that's because it's dependent on the x direction because there's a wall there. So friction force of the wall is what's slowing down the liquid. Um, like going back up here. In the z direction alone, which is this direction, like this direction, the fluid is not um, changing speed in that direction. It's changing speed in this direction. So you see where the fluid is closest to the wall, which is this line here. Its slowest, it actually is zero velocity at the wall. So it moves at the same speed as the wall. So if the wall was moving, it would move at the same speed, or would move at that speed of the wall. So since the wall is not moving, it's just staying still, and then the maximum velocity is up here, farthest away from the wall. And so yeah, we eliminate that term, and then we eliminate the rho VZ term. Well, not super eliminate because going back up here again, because the velocity is not dependent on z, the rho Vz times Vz minus rho Vz times Vz from this term, that will cancel out because they're the same value because the velocity is not dependent on the z direction. So yeah, so at z equals 0 and z equals L, they're the same value. And then the pressures are the same because they're both exposed to the atmosphere, so at any height. So if there was a pipe and it wasn't exposed to the atmosphere, they would not be the same. But obviously that's not this problem, so I might be talking about it. So now going to the momentum flux in the zx direction. Again, this is wrong. It should be zx, not xz, but it doesn't matter because the definition is the same. So that is, again, going back to the top, or these definitions. As you can see, there's no p in this, so it's the t zx plus pvx vz. Or where is it? Okay. So yeah, the Vx goes to 0 because obviously there's no velocity in the x direction. There's only velocity in the z direction. And the tau Zx equals this from, where is it here? It's right here. Okay, so yeah, tau Zx equals tau Xz. So they're interchangeable because obviously, look at this formula. It's like you just switch one, yeah, whatever. So yeah, that's where you get the formula, table B1, which is on page 843 if you want to look at it yourself. So dvx dz, that goes to 0 because there's no velocity in the z direction, or no velocity in the x direction. So yeah, then you plug those terms back in and into the expanded direction, and obviously this thing right here, this top thing would be 0 because there's no differential pressure at all because it's exposed to the atmosphere. So you get this, and then use the definition of a derivative, which the definition of the derivative is the final value minus the initial value over the final position minus the initial position, as long as it's linear. If it's not linear, you can't actually just like write this out. Well, I mean, you can for this case, but I don't even know what I'm talking about that. Just disregard. But yeah, so basically the sign changes because if you look at this term, which is canceled out, the z equals L, that's the final position. So this would be here and that would be there. So it basically just puts a negative sign out from front of this. So like if you have a term on the other side, it'll mess with things. So this is going to be like doing the derivative operation. This is going to be a negative here. And this is, well, obviously you'll see here. Okay, so yeah, as you can see that I took the negative here from here. Like there was a negative here before, so that's where that negative disappeared to. So there's usually a negative out front, and from this definition here, there's a negative. But that disappears because when you convert it to a derivative, the sign flips. Yeah. So again, this is useless because, yeah, for this problem because there's no differential pressure because it's supposed to atmosphere. But I mean, you can like, I just set the term equal to 0 at the end because it doesn't really matter. Which, if you're gonna do this yourself, just do the problem without ever having this term here, which it's fine. So then we're going to find the boundary conditions at x equals 0. Again, that's what's the best drawing for this? At x equals 0, vz equals 0. So that's again, where's the drawing? Where's the drawing? So that would be like here. Um, so that's the law of the wall. Um, that's a boundary condition at the front of the chapter 2. And that basically just says the velocity is the same velocity as the wall, and the wall velocity is 0. So it moves at the same speed as the wall. And yeah, so it's boundary condition A in section 2.1. So you could just look at that and read that. Basically, it just says the same thing as I said. And the second boundary condition at x equals sigma, um, the shear stress equals 0, and this is because if you go back up to that drawing again, it's because this is the max velocity. So if you take the derivative of velocity, it's dvz dx, and um, at a maximum, the derivative will always be 0. So that's like finding derivatives or finding solutions that you do that. Find the derivative and solve for 0. That's usually a max or a local max, but in this case, there's only one thing, so it's just the max. So now we're just isolating the derivative term, and we're taking an integral. So yeah, so that's, you just multiply the dx over, and again, the pressure is, I'm just going to pretend that the pressure is like that when it's really not. Normally it'll just be C1 here for this first integration, but obviously that's not what I did because I'm an idiot. Um, but yeah, so it'll just be this for this idiot wrong version. So yeah, then we employ the second boundary condition. Well, we isolate. Um, Wait, did I even do this right? Oh, I think I went back and changed it because. Oh no, so there should be a U here. There should be a U here, but I think it turned out fine. Yeah, there should be a U in the denominator here, but I just didn't put the U there. So yeah, normally you would just isolate. Well, does it even matter? No, yeah, I think it does matter. Yeah, normally, yeah, just isolate that. You would isolate the derivative and then employ the boundary condition. So it would be 0 um, dv dz or dvz dx would equal 0, and then why am I even doing this like this? This is so weird. No, at x equals sigma, dvz dx equals 0. So this is the dvz dx, and then the x is normally here. The x equals 0, or the x equals sigma, and then you solve for the C1. So C1 equals negative modified pressure 0 minus modified pressure L over, or times sigma divided by, it should be UL because I forgot to divide the um, viscosity here because I don't know why I did that. But okay, so yeah, look, I reinserted it the correct way. I don't know why I didn't do it right at first. So yeah, dvz dx equals that. And a lot of the times you won't be able to do a boundary condition or like do a boundary condition mid integration process. So like if you have a derivative boundary condition, you'll be able to do it mid integration process. But sometimes you won't have a derivative boundary condition, so you'll just have to integrate it twice with two um, integration constants and then do the boundary condition. If you have two just plain velocity integration constants. All right, so yeah, so we integrate again, just integration. It's pretty simple. Yeah, just do that. So then we employ a second boundary condition. This is the law of the wall boundary condition. So at VZ or at x equals 0, VZ equals 0. So we plug in all the zeros for VZ and then the zeros for x, zeros for x. And then we solve for C2 and we see that C2 equals 0. So we could plug in 0 for C2 and then we get this VZ equals that. So then we simplify um, and we get that. And that's just by lumping these terms together. So you see this common term here, um, modified pressure, um, just this term here. Can I draw on this? How can I draw on this? I don't know. But yeah, so we see these lump terms here, and we could just lump them together and multiply all the excess terms. So it's x, and then we have the x divided by 2 for this thing, and then, yeah. So then I'm converting the modified pressures back to expanded form, and that's because I was an idiot and used modified pressure in the first place, so I had to convert it back so that this would separate, and when I set the pressure equal to 0, it wouldn't just like zero out the whole problem, because obviously that's not the answer. So yeah, this definition is right as long as the coordinate system is from bottom to top. So if the coordinates are from, like if the coordinates are top to bottom and they're going down with gravity, then it would be the modified pressure equals over L equals the pressure difference over L minus rho GZ. So, but obviously since it's not the case, it's fine. And it's equals cosine B because um, GZ is the gravity due to the Z direction, and the Z direction is found through cosine B. Um, that's just back to the drawing earlier. The Z direction, if you take the cosine of that angle there, you get the vertical direction. All right, so this is the separated version. So we get this, and then here I just realized that, oh yeah, a pressure term is just not there because I'm an idiot. And we get rid of that term, and we could just get this expression here. Yeah, so I'm just manipulating the variables to match whatever it says in the textbook answer. So I'm just taking out that extra x that I had in there, putting it in there, and then I'm dividing sigma squared out of the um, parentheses here and putting it outside of the parentheses. So if you can divide um, you can divide this, you can divide sigma from the parentheses, but you have to multiply it outside. So yeah, that's what I did. And then again, more simplification. So yeah, x squared over sigma squared is equal to x over sigma in parentheses squared. That's just a thing that you gotta know. So yeah, and then yeah, that's the equation. Final equation there. And that's the same equation that we get. So part B. All right, so for 2B1, turns out there's a second part. It's this show how equation um, you can get equation 2B1/1 from 2.2-18. So 2.2-18 is this equation here, and I wrote it in, oh my god, I have to go to Google Drive. I wrote it down right here. Oh wait, where is it? 2-1. No, it's just right in the last. Okay, so 2.2-18. So yeah, I wrote it right here. And in our system, since the coordinates start from the plate surface and not the liquid surface, x bar, the x bar of the coordinate system that is the new coordinate system that was just for this problem equals sigma minus x. So going back up to the drawing, okay, sigma is the length of the liquid, like the height of the liquid. So if x is from up here to down here, um, sigma x bar is sigma minus x. So this whole thing is sigma, and then x is this. So as x is increasing, x bar is decreasing. Yeah, that makes sense. So yeah, yeah, that makes sense. So then basically just go back to the 2.2-18 and you insert that definition sigma minus x bar in for x anywhere that it is, which is just right there, I think. So then, yeah, do that and then expand the polynomial there. And do some algebra to make it into this. And then the ones cancel, and you get back to your equation that you solved for earlier. This is the same as this here, so you know it's right.